We're back here on The Rocketry Show at TheRocketryShow.com. CG and Jeem, and got another cool team here that was finished up just not too long ago here at TARC.
Yeah, we got a team from SoCal here. So if you guys on the microphones, we'll start with you. First name and just first names, so we don't need any last names. And then tell us a little bit about where you're from, the name of your team, and what school you're at.
So we're with West Rocketry. That's our team name, but we're with a nonprofit organization called Springs of Life Christian Fellowship.
Awesome.
Yeah.
Awesome. Yeah, very cool. So, and what's your name?
I'm Kelly.
Hi, Kelly. So we have a rocket in front of us here, and we're getting some video of it as we speak. Now, is this the first time that you guys have competed in the TARC competition?
Oh, no. This is my 5th year competing.
Oh.
Yeah, this is my 3rd year, and this is Allie's 1st year.
So you guys are all pros at this then, huh?
Yeah.
So tell us a little bit about the rocket here. It's got some interesting features to it, and this is your time to tell us about it. So go ahead.
Right. Great. Well, I'll just kind of start with the top down. So the whole rocket is made from carbon fiber. So this is a spread toe carbon fiber that is it's the same fabric that most Formula One racing teams use. SpaceX also uses it. But we're actually vacuum bagging all of our components. Most teams here are just wrapping around a mandrel and letting it cure.
Right.
So this is actually vacuum bagged. You have a lot better compaction and way better resin content. So where a standard wet layup will be 1-to-1 ratio of resin to fabric, this is going to be about 37%.
It's
in
beautiful.
relation to fabric.
That's absolutely beautiful. And now, obviously, you went with carbon fiber for strength, but what weight advantages do you see out of that?
Well, so it's extremely lightweight. Basically, the lightest commercially available tubes are supplied by Estes, and while they're great, they're susceptible to moisture. They're not very strong, and they're just not great to work with. They're not very durable. Whereas carbon fiber, it's incredibly lightweight. It's lighter. It's not affected by humidity, and the durability is just unparalleled.
So you're saying that a BT60 tube that from Estes is going to be heavier than one that you did vacuum bagged on your carbon fiber?
Correct.
How much? What's the difference in weight on that roughly?
About 33% lighter.
33% lighter and stronger.
Well,
boy, that sounds like a no-brainer, doesn't it?
Yeah.
Yeah.
How much flight testing and how about the design? Well, let's start with the design process on this because it looks like you've got a smaller section, bottom section than most teams. And can you tell us a little bit about that and the transition? Because the transition seems to be longer than what most teams have been doing as well.
Right. Okay, so the whole design concept was to be as space and weight efficient as possible. So not necessarily lightweight, but just efficient with it. So we were trying to remove as many components off the rocket as possible. So right here, you can see the tube is much smaller, like you were saying.
Right.
That's 24 millimeters on the inside and about 25.5 on the outside.
And that's the lower airframe for everybody out there, where it's usually, as you know, the TARC it's a 2-diameter rocket. The smaller tube is the one with the fins on, so the top section is one with the payload. So just for all you out there listening. Okay, so 24. So that is interesting. That's going to affect your motor choice, isn't it?
Well, yes and no. So we designed.
It always is that, isn't it?
Oh yeah. So we actually chose this after selecting the motor. As far as design ideas and theory, we started with the motor. We love the F79 motor. We've used it for the last 2 years.
F79, wow.
F79, lots of power.
Yeah.
And the really important part is the quick burn time.
Right.
So the faster you can get up to speed, the more stable it's going to be, and the more resistant to wind.
Absolutely.
So that's why we're using an F79, and so with that, it's 24 millimeters 3-grain. So that's what dictated the size of the motor tube here.
Okay, and I also see an interesting feature on the fins there. Can you tell us a little bit about that?
Okay, so those are the wedges. So they're
wedges.
the wedges, yeah. So for the last 2 years, so we've had a 3-year program of Highdrag boosters.
Right.
The last 2 years, we've been actually canting our fins in 2 sets. So it doesn't rotate in a sense, but they're angled against each other to create lots of drag and works similarly to a wedge. And that works great. The only problem is you're limited to 4 fins. And you have to, the skill required and the time it takes is just not reasonable. So these wedges provide the same effect. However, they can be put on in a minute versus taking 3 hours to mount a set of fins.
So what are you using those for? Just added drag to slow it down if it's with that motor, or?
That's a factor, yes. But the real big point is to move the center of pressure further down.
Okay.
Where a standard rocket, if you didn't have these fins, center of pressure would be, I don't know, more or less close to about here on the rocket.
Right, which is about the midsection of the transition or so.
Right, yeah. So, but with these wedges, these are 6 millimeters across on each side. It moves the center of pressure almost to the end of the body tube.
Okay.
So the stability from it is just amazing.
So that'll just give you a straighter, more stable flight just by doing that.
Correct. We don't have to adjust anything for wind up to 20 miles an hour. Nothing changes.
That's pretty cool. And I assume that you flight tested that in 20-mile-an-hour conditions.
Yes, we did.
Clever.
Mm-hmm. That's pretty amazing engineering. I mean, how did you guys come up with that idea?
Well, as far as the angled fins go, that's when we first started and first realized how resistant it was to wind conditions. It was on a drive home from a meeting. I was talking with my dad, and I was thinking, like, what if you just kind of angled them against each other? I wonder if that would slow down the rocket. And then it wasn't until after testing in the wind that we realized the wonderful stability that came along with it.
Very, very
cool. So it was
cool.
really almost just an accident.
It's actually that's an innovation that I haven't seen yet around here, and that's very cool. So to your credit, you guys have like your vacuuming tubing, carbon fiber, and vacuum packing, and wedges on fins to move the center of pressure back. So what other fun features are on this that I don't know about?
Oh well.
Now that you ask,
now we're into the fun part.
Absolutely. This is your time to shine, guys. Have at it.
So most rockets, they depend. How's the audio good? They rely on the total apogee for their scoring.
Yeah.
And that's great. That works great. You can get accuracy of about 20 feet if you're good.
Right.
That's where I was 3 years ago. But I wanted to get a little better. So with a little coding, some 3D printing, and a lot of time, put together a spring ejection system.
A spring ejection system. I'm holding in my hand. It looks like it's a 3D printed.
Oh, you can pick it up. You move it around.
With maybe an 800 mAh battery. It looks like 2 cell. It looks like it is a stack of standard off-the-shelf type parts. Can you tell us a little bit about that?
Of course.
Okay.
So that whole stack that you're looking at right there is Tiny Circuits Arduino Uno.
Okay.
It's a full Arduino Uno, but in that small package. So as far as processing ability, it's fantastic.
Hey, we know the people who designed that.
That's right, we do.
So we're able to read the pressure 20 times per second along with oversampling. So it's incredibly accurate and precise. That sensor is accurate to within about 3 feet, as far as our testing shows.
That is amazing. And then so everything's set up, and then the spring will bounce it off. This is amazing engineering.
Oh, thank you.
I mean, this really is. Do you want to see a shot of that with the spring? I think that the photo of this needs to go up on the website as well. You guys are amazing. This is so cool.
So that was many late hours designing, getting frustrated at Fusion 360, just like, why won't you fit?
I believe it. So how long did it go from how much of a part did everybody play in this as far as like the team goes about the different design aspects and different actual production of this?
Right. So as far as design goes, I really try to include my other teammates.
Yeah,
I've been doing this for 5 years. So I'm pretty familiar, but a big part of it is I want the team to keep going.
Right.
So as far as just keeping everyone involved in the design process is what I was really hoping for. So one of the big things Kelly put together was we were trying to figure out a solution for the motor retainer.
Yeah.
With a minimal body airframe, or it's what it's called, there's no place to mount a motor retainer.
Right.
So we were talking about it, like how can we fix that? How can we do that?
Yeah. What are you gonna do? Right.
Yeah. What are you gonna do? And I didn't want to friction fit the motor tube because it's just not reliable.
Right.
I can't take the chance of it ejecting it,
Right, absolutely.
in flight.
It was really funny. I just kind of looked at everyone. I was like, okay, is this dumb? Should we just glue it in? And so we epoxied the motor casing in.
You know what?
If it works.
It works.
It works.
So you have to clean it out after every launch then.
Right.
But that's not a big deal with a 24 mil.
Yeah. So we just have a steel rod. We just eject the spent motor and load a new one in.
Poke it through and you're good to go. Wow.
We have our rail that we poke
that's
it through.
beautiful because on this rocket, as I'm looking at it for everybody out there, we've got a very simple, easy solution for the motor that they prefer to use. And it looks like that's a Cicerone load, so it's easy to clean.
Yeah.
So it's not and we've got this incredibly beautiful and complex spring-loaded ejection system. This is the best of both worlds on this rocket. There's so much engineering in this one rocket that I'm looking at that I'm just thoroughly impressed with the work that you guys have put into this. You should be really proud of yourselves.
Thank you.
I mean, I'm looking at this thing going, yeah, I couldn't do that. I'll do something else.
It's really not that hard. Just takes a lot of time.
I know, but just to think it through and to work the problem like you guys did.
Right.
That's really awesome. I mean, I'm kind of like the sledgehammer kind of rocketeer guy that likes the big power and just I'll make it big and strong and fiberglass and it'll be good. It is. Well, and CG does a lot of modular design stuff. So
that's great.
He does a lot of intricate design work and everything, and it's kind of nice to see.
Well, you see, it's the best of all the work because you see me jumping up with my camera taking pictures. So
it's absolutely a beautiful rocket. So how did you guys do?
Well, that's the part.
I'm sorry.
So one of the So we started 2 years ago with this whole program of controlled flight with CO2 ejection, and that works great. Only problem is it affects the scoring altimeter. I'll show you right here.
Oh yeah, the pressure change.
Right, so the pressure change
inside the bulkhead.
That's up in here. Yeah, it just finds its way around, and that will corrupt the data.
Okay.
So we had to move away from that, and that means that there's no for sure way to inflate the parachute other than the airspeed.
Okay.
So that's what we were using. The CO2 inflates everything, gets everything out.
Right.
Super
Kick
consistent.
it out fast. Blah blah blah.
We were getting consistency of about 3 feet, plus or minus.
Okay. Pretty good.
Pretty good. So now with the spring ejection system, you have to rely on airspeed to inflate the chute, and that's just not reliable. So what happened is the parachute got caught slightly in the coupler, so it took a little longer to deploy.
No. Yeah.
Everything deployed. It was a beautiful flight, though. It was great. So it went about 20 feet high, and because it was higher, the duration was longer.
Right.
So we got a score of, I believe it was like 50.3.
Okay.
So
okay.
Not great.
Not great, but not bad. No
Right.
slouch at all. I mean, that's really cool. I'm just in awe of this rocket, guys. This is really cool that you did that.
Thank you.
So I'm just sitting here going, okay, I'm not worthy of that, but time to go back to fiberglass and L motors.
There's nothing wrong with fiberglass and L motors.
So, but is there anything else that you would like to talk about while you're here with us?
I mean, sure, we can keep going up the rocket.
Hey, you know what? Go.
Or we're not done yet. Wait, there's more.
Go for it.
Yeah, so up here, over the last 5 years, really, we were just never happy with the way the whole payload section was designed. It just wasn't great. So we spent a whole lot more time on this year, really trying to make everything great and perfect and make sure everything has its place. So the altimeter sits in a nice little section that it's in.
Okay.
And it gets covered with foam and it's taped down.
And that's the official Firefly or whatever.
Right. Yeah.
TARC
So this is a peanut. Yeah.
Same thing.
Yeah. So it's so it being taped down. We don't like using tape, but tape is easy, cheap, works well. But basically to reduce the total amount of airflow. It's just reducing noise, trying to get it really clean numbers.
A little damper.
Yeah. So that works really well. And then most teams, they're either using a friction fit nose cone or they're putting screws in.
Right.
And neither of those are really ideal. Friction fit, you run the risk of it falling out after flight if you have especially hard ejection like we do.
Yep.
And with screws, you're just taking lots and lots of time.
Right.
So we designed a toolless system that just locks in and you're ready to fly.
Oh, nice. Just a rotate lock.
Yep.
Yeah.
Everything works in nice and pretty. And then back here you can see there's a bulkhead that's actually removable. This whole area is lined with foam. Here. I can actually take it apart if you like, but
3D printed.
Yeah, everything. I just discovered 3D printing.
This thing is more modular than you thought, isn't it?
See, you're all over this now.
Yeah. It's funny you talk about modular. Everything as far as that's been 3D printed is designed to be interchangeable. We brought 2 rockets here today and a whole other rocket in parts. So we could assemble it in maybe 20 minutes. That's a rocket.
See, you know how I am about the modular stuff, you know.
Absolutely.
I have a disaster and people go, wow, wait, you could just put a new piece in there. Yep, that's it.
Yeah, I'll just take this out. It'll be done in 20 minutes. It'll be fine. I'll leave it on the bench for a while. It's going to take you longer to clean your motor than it would be to actually do the repair.
Yeah, it's funny. So 2 days ago, we practice launched out here. So we flew in a couple days early, wanted to make sure everything was calibrated. And we didn't quite lose our main rocket, but it had some problems. What happened is the cold weather. So in California, it doesn't really get that cold.
Right. I was going to say, the weather conditions are way different here.
Way different, right. So it was colder 2 days ago than we've ever launched before. And what happened, the PLA shrunk to the point where when it took off, as soon as motor burned out, air drag ripped the booster off and deployed the parachute at about 300 miles an hour.
Drag separation.
Yeah.
We know that one.
Yeah.
You should see with a 50-pound rocket what that looks like. It's not pretty.
Yeah, I'm sure. So we actually lost this whole bottom part of the ejection system, but about 20 minutes we had everything put back together, flew again.
I mean, it's elegant and it's simple and it's just beautiful.
And it's running right now, Gene. It's running right now.
Oh yeah, it's on. It's on. It's ready to go.
I know. Simply elegant, and it's on. Oh no! That is really amazing, guys. This has been fun. Is there anything else you want to talk about on the rocket, or anything at all?
We've got one last little thing to go.
Absolutely. There's another part there, and I got it this time.
But wait, there's more.
Absolutely, this is awesome.
So the nose cone on here, we were just gluing them on to this coupling piece.
Yes.
And that works great. Nothing falls off. It's easy to use. Only problem is alignment. You can sit on the bench and you can make sure it's as aligned as humanly possible. But when you go and you put it on the pad, you step back. It's crooked.
Yeah,
right.
Gotcha.
And then another problem is you can't swap out foam all that easy. This is designed to fully encapsulate all the foam, which it lasts for almost 20 launches. Only problem is you can't replace it when it needs to be be refurbished.
Right.
So these bolts on the outside here, it's a little time consuming to take apart. but there's basically rails on the inside. So if you were to loosen these, you can pivot this to about maybe 5 degrees.
So you get a little play as you need it.
Right, and then if we need to replace the foam, we can take everything out and disassemble the whole thing.
And what we're talking about for the listeners, it looks like the shoulder on the nose cone, and it's actually movable and stoppable, so that it's a two-piece, or it's more than two-piece, but essentially for radio purposes, it's a shoulder and a nose cone with all kinds of cool stuff on the inside. But it's mounted on rails that they can actually adjust the exact point of the nose cone based on where they are and where it is out in the field and what it looks like. So it can always be self-leveling almost, with a little help.
Yeah. With a little help, yeah.
So that is so cool. That is an amazing rocket. I mean, it keeps going on and on and on. There's so much engineering, so much thought into it that you guys, hands down, this is probably the coolest engineered rocket I've seen.
Great,
I got to tell you. So. All right. Well, thank you very much, guys.
Thank you.
And sorry it didn't quite work out the way you wanted it to for that first rocket.
It's all good.
But I'm glad that it's like students like you that make the old guys like us say, okay, this is cool, and it's cool that it's continuing on with you guys. So thank you for that.
Taking it to a new level.
Great. Thanks.
So, thanks, gang.
Thank you.